You know, some of the greatest stories in science come from the most unexpected places. And this is one of the best. It's a story that starts with a spectacular failure, kicks off a century-long hunt for an invisible ripple in reality, and ends with humanity gaining a brand new sense to perceive the cosmos. So where does it all begin? With an event of just unimaginable power. Picture this: two black holes, each one dozens of times more massive than our sun, caught in this gravitational death spiral. As they whip around each other faster and faster, they are literally churning the fabric of space and time. And then, bang, they collide and merge, unleashing this incredible burst of energy. But it's not light, it's not heat, it's ripples in space-time itself. These are gravitational waves, something Albert Einstein dreamt up on paper 100 years ago. And the thing is, scientists knew that if we could ever detect these waves, it would be absolutely revolutionary. As one source put it wouldn't just open a new window on the cosmos, it would smash the door wide open. A whole new way to see the universe. So that's the big question, right? How in the world do you build a machine sensitive enough to feel a vibration in space-time? Well, the answer, weirdly enough, starts more than 100 years ago, with a hunt for something that wasn't even there. Let's rewind the clock to the late 1800s. Physicists had this huge puzzle on their hands. They knew light acted like a wave. And, waves need something to travel through, a medium. Sound has air, ocean waves have water. So what was carrying light across the empty vacuum of space? They came up with an idea: the luminiferous ether. This was supposed to be this invisible, all-pervading substance that filled the entire universe. Every star, every planet was just moving through this kind of cosmic jello. But the properties they imagined for this ether were, well, they were completely bonkers. For light to travel so fast, the ether had to be unbelievably rigid, more rigid than steel. But at the same time, for planets to just glide through it, it had to have basically zero resistance. It was a total paradox. Still, they figured, if it's real, then the Earth must be moving through it, creating a sort of ether wind. So, in 1887, two American scientists, Albert Michelson and Edward Morley, set out to build a machine to finally prove it, to detect this ether drift once and for all. And this is it, the Michelson Interferometer. And the idea behind it is just genius. You shoot a beam of light at a special mirror that splits it in two. Those two beams travel out at right angles, bounce off other mirrors, and then come back to recombine. The logic was, if there's an ether wind, the beam of light traveling into it should be slowed down, arriving back just a fraction later than the other one. They were expecting to see this specific interference pattern when the light beams came back together. They ran the experiment. They rotated the whole apparatus. They checked everything over and over. And what they found? Well, nothing. Absolutely nothing. No drift. No change at all. It went down in history as the most famous failed experiment of all time. But here's the twist. This failure was actually one of the most important discoveries in the history of physics. It meant the ether didn't exist. There was no universal at-rest frame in the cosmos. And here's the really mind-bending part. It meant the speed of light wasn't relative. It was constant. The same for every single person, no matter how fast they were moving. This one, bizarre, beautiful fact that the speed of light is absolute, was the key that a certain young patent clerk in Switzerland needed to completely rewrite the laws of physics. So in 1905, Albert Einstein basically took the result of that failed experiment and made it a cornerstone of his new theory, special relativity. He just laid it out there. 1, the laws of physics work the same for everyone. And 2, the speed of light in a vacuum is constant for everyone. From those two simple ideas, everything else fell into place. Time dilation, space contraction, E=mc², all of it. And then, 10 years later, he gave us his masterpiece, general relativity. He said gravity isn't some mysterious force. It's just what happens when mass and energy literally bend and warp the fabric of space-time. The Earth orbits the sun because it's just following a curve in spacetime that the sun creates. And a wild prediction of this theory was that huge, accelerating objects should create ripples in that fabric, gravitational waves. For 100 years, that was just a prediction. These ripples were thought to be so unbelievably faint that Einstein himself was convinced we'd never, ever be able to detect them. But physicists, they love a challenge. Meet LIGO, The Laser Interferometer Gravitational-Wave Observatory. You can think of it as the great-great-grandchild of that little tabletop experiment from 1887, except this one is built on a truly epic scale. There are actually two of these massive facilities in the US working together. And the incredible thing is that the basic idea is exactly the same as Michelson and Morley's. A laser gets split, sent down two arms, each 4 kilometers long, and bounced back. If a gravitational wave from space passes by, it will stretch one arm and squeeze the other by a distance that is 1/10,000th the width of a proton. I mean, it's an impossibly small change, but LIGO is sensitive enough to see it. When you put them side by side like this, you can really see the scientific family tree. On the left, the simple little device that failed to find the ether but found something way more important. And on the right, it's modern air, a machine so precise it can feel the collision of black holes a billion light years away. Same core idea, just separated by 128 years of incredible science. It all comes together in this just beautiful story arc. It starts in 1887 with the failure that sets the stage. Then Einstein comes along in 1905 and 1915 and gives us the theory. And then, a full century later, on September 14th, 2015, after decades of work, LIGO hears that first faint chirp from two black holes colliding. They'd done it. So, yeah, the discovery won the Nobel Prize, of course. But the prize isn't the end of the story. Not even close. It's the beginning. So why is this such a monumental deal? Think about it. For all of human history, every telescope, from Galileo's first little spyglass to the Hubble Space Telescope, has studied the universe using one thing: light. The entire electromagnetic spectrum. We've been watching a silent movie of the cosmos for centuries. But here's the crucial part. This is the whole game changer. Gravitational waves are not waves traveling through space like light does. They are waves of space itself. It's the actual fabric of the universe that's vibrating. It's a totally new kind of information, carrying a totally new kind of message. Detecting these waves means we are no longer just watching the universe. For the first time, we are listening to it. It's as if a species that had been deaf since birth suddenly gained the ability to hear. We can now perceive these insane, violent events, like black holes crashing together, that are completely invisible, that give off no light at all. We have a new cosmic sense. That beautiful failure back in 1887 accidentally handed us the key. 100 years later, we used it to build a giant ear to listen to the symphony of the cosmos. And we've only just started listening, so the really thrilling question